Thank you everyone for joining today.
Where are the office bearers? Are they not present?
Today,
Shantanu?
Santanu Bose, Professor Santanu Bose is traveling. He said he will try to join.
Okay.
Santanu Mishra, I am not too sure about.
Okay.
But yeah, it's already 3 minutes past 4. So, Anupam,
I think,
should we start
yeah,
or?
we should start. We should start.
Yeah, okay. So, today we have Mr. Deep Das, a very young researcher with us. He's a final year PhD student here at IISER Bhopal, and he's going to share with you on a topic reflection on the active tectonics of the Darjeeling Sikkim Himalayas. And he has done his graduation and masters from Jadavpur University, Kolkata, and is here since 2018. So, with this brief introduction, may I now invite Deep to present his work. Deep, the floor is yours. Go ahead. Unmute yourself, please. Unmute.
Sorry, I forgot about that.
Go ahead.
Is it visible?
Yes, everything is fine. You start.
Okay. So good afternoon, everyone. Today I'm going to talk about as Dr. Jyotirmay Mallik said, that I'm going to talk about my research, my PhD research, which is on reflection on the active tectonics of the Darjeeling Sikkim Himalayas. So first of all, let me introduce the area. Introduce the area. So this here, the Darjeeling Sikkim Himalaya lies in the Indian state of West Bengal, northern part of the Indian state of West Bengal, and it's hello, hello.
No. It was fine just 1 minute before.
Now,
Yes, now it's fine again.
okay. So I'm audible now, right?
Yes.
Okay. So this Darjeeling Sikkim Himalaya lies on the Sikkim Bhutan seismic gap. So by seismic gap, which it indicates that the area haven't experienced any major earthquake since last century. So according to the Gutenberg Richter law, a greater earthquake is due in this region. But still, we see some a small magnitude earthquakes here. This can be explained by the elastic rebound theory, where the applied stress, when the applied stress exceeds the material strength, in that case strain energy releases. But in the in between period, the hello.
No, go ahead. It's okay.
Okay. Sorry. Say, so where was I? Also, yeah. So when the energy suddenly releases, it causes any great earthquake. But in the meantime, when the strain is building up, it sometimes the area releases strain in small amount, and this causes the smaller earthquakes in the region. Now, in terms of structure, so we can see there are several north dipping thrust within the region, and all the thrusts are branching out from the basal main Himalayan thrust, or the MHT here, and there lies a duplex structure also between the Ramgarh thrust and the main boundary thrust, known as the Lesser Himalayan duplex, and in the area it is known as the Rangit window, which is situated here. And this is the balanced cross section from Bhattacharya et al. Of the duplex structure. Now, to understand the ongoing tectonism, so I subdivide. So this is to understand the tectonism. So I tried to understand the cause of the tectonism by using sandbox modeling. Then the manifestation of the active tectonics is studied with the recent surface stress orientation and river morphometric changes. And the effect of the active tectonics is studied through landslides and reservoir triggered seismicity. I didn't study this large scale seismicity because it's another topic on its own. And combining the results from all these studies, I tried to give an overall kinematic model of the study area. Now, to do that, I subdivided my study with 6 objectives. So first one is the recent stress orientation around the Darjeeling Sikkim Himalayan region using FEMR technique. So let's go to the objective number 1. So here as the objective title suggests, that here I try to determine the maximum near surface maximum horizontal stress direction, and then to understand the zone of active deformations. So before going to that, let's talk about the methodologies and how the fracture induced electromagnetic radiation functions. So in a fracture basically indicates a microfracture basically indicates separation of bonds. So due to the bond separation, bond breaking, we see the separation of charges, and due to this newly created imbalance within the system, the dipole moment between these two ions, between the ions, releases EMR pulses, and as we move farther from the crack tip, we see that this amplitude decreases because the distance increases from the crack tip. That's it. Now I'm talking about microfractures. So how can we correlate this microfracture with the large scale tectonics? So this can be explained by this example. So suppose we are applying stress within a rock body. In that case, several microfracture will form and it will reorient itself according to the stress direction. Then with increasing stress direction stresses, uh, the microfracture density will increase. And here in this diagram, we see that the pulse voltage also increases up to that point. And after certain time, so these microfractures will coalesce and give rise to a macro failure. As soon as the macro failure generates, the amplitude drops suddenly, as you can see from this diagram here. Now this is the device which has a receiver antenna, and this is the processing unit, as well as it displays the data, and these are the technical details of the instrument. Now what I did, I put the antenna horizontally and reorient itself with the geographical north. Then after and then at every 5 to 10 degree intervals, I measured the EMR pulses, and based on the mode of fracturing, this two kind of polar diagram can be observed. So for the shear fracture, in that case, we will see this bidirectional bidirectional lobes, and the acute bisectrix of that gives the SH-MAC orientation, whereas for a mode 1 fracture, this is the SH-MAC orientation. Now based on that, so here we can, what we can see in the left hand side diagram, the regional stress is more or less arc perpendicular throughout the Himalayan mountain belt, and in my study area it is around north 7 degree. But if you give a closer look, in that case we see that the stresses have reoriented itself at several places. Some places it is perpendicular to the fault plane, and at some places it is parallel to the fault plane. So this can be further seen in this diagram here. So here we see that some of the stresses have some of the stresses are stress directions are parallels or to subparallel to the thrust strike, whereas at some places it varies quite much. Now if we talk about the seismicity of the area, so most of the seismicity is restricted between the MBT and MCT, and this is where the Rangit window lies here. Now, so what we see that the recent near surface recent stresses have reoriented itself and became parallel to the thrust strike near the Rangit window region. Now, if I look at the slip tendency analysis of the fault planes, what we see that, so what I did at first, so I from the measured stress direction, I interpolated those stress for the whole area, and then by using the mutual relationship between the stress azimuth and the thrust strike, I try to determine the slip tendency here. So here we see that some places the slip tendency is quite high, indicated by the red color. At some places it is low, indicated by green color. But in the Rangit window region, what we see that the stress slip tendency is very high throughout the whole region, and these white dots indicate a co-seismic landslide. So these co-seismic landslides, these landslides occurred after 2011 Sikkim earthquake. So here we see that most of the landslides are concentrated within the Rangit window region, and in other places it is dispersed. So what we can understand, so if I look at the slope distribution of the landslide, we see that the most of the landslides are restricted within 30 to 40 degree slip. And Larsen and Montgomery 2012, they also proposed that for Himalayan region, so based on study in other parts of the Himalaya, so in Himalayan region, what we see, this particular slope indicates that landslides due to tectonism. So that from this we can, we can say that this area is tectonically active, maybe tectonically active. Now if we look at the swath profile of the region, in that case what we can see, so here is the swath that marked by this rectangle here. So in this swath profile what we see that the Rangit window region has lost significant taper. So according to the taper wedge theory, the area will reach its critical taper, and till then the area will uplift. So from this, what we can say that the Rangit window might be is the active structure or the active zone in the region, and this is because of the enhanced erosion by the combined effect of Tista River as well as Rangit River. Now, this study was published in the Journal of Structural Geology in 2021. Now, moving to the objective number 2, which is understanding the response of active tectonics on regional rivers. So, firstly, I've chosen this the West Sikkim and the part of the Darjeeling district. So this is basically the Rangit River catchment. So as my objective number 1, I have identified from the stress orientation as well as landslides that this area might be an active zone. So I wanted to study how this activity affects the drainage morphology within the area. So the objective was for this study is to determine the effect of active tectonics on the river channel evolution, as I have already mentioned, then determining the zones of deformation localization, and then to finally test the effectiveness of the popular morphometric indices on decoupling the effects of lithology and tectonics. Why I am saying this? Because in most of the studies, what we see that uh, most of the authors, they consider the rock strength or the erodibility of rock based on their origin. So for example, metamorphic is the hardest rock, whereas sedimentary rock is the softest rock. And the river, this is a typical river channels, river long profile. Here we can see segmented long profile, and each segment follows this particular equation, and the variation within the segment can arise either because of erodibility of the substrate lithology or due to the spatial variation of uplift rate. Now, let's talk about the the methodology. So, for this study, I have used these two equations. So, this S indicates slope, KSN is the steepness, and A is the upstream drainage area. And here, same equation can be rewritten as U by K. So, U is the rate of uplift, and K is the erodibility of substrate lithology. And I tried to find out this kind of structure within the river long profile slope break nick points. This indicates a possible perturbation due to tectonism. Now, comparing these two equations, what we can say that the steepness is inversely proportional to rock erodibility, and it is directly proportional to the rate of uplift. Another morphometric index that I used, which known as the hypsometric integral. So this hypsometric integral and the hypsometric curve, this is the curve here. So this curve indicates the stage of the river catchment and its maturity. So if I see a concave curve here, so this curve indicates a mature basin, whereas a convex curve indicates a younger basin, and a concave convex curve, as you can see here. So this indicates that the river catchment is still adjusting to the last phase of uplift, and any older river can be shifted towards a younger river by any tectonic perturbations. Now, so as I already mentioned that to identify the effect of substrate lithology as well as uplift, I proposed a new morphometric index known as volumetric change metric or the normalized stiffness ratio, sorry, relief ratio. So here what I did, I sampled the maximum and minimum elevation using grids from a digital elevation model, and then based on the maximum data points, elevation data, I prepared a summit level DEM, and based on the minimum elevation, I prepared a base level DEM. And using this equation, I I try to understand the erodibility of the rock. So the assumption here is the harder rock will resist erosion. It will try to maintain its original form, and it will remain as a paleo landform, whereas any softer rock will achieve its base level of erosion at a faster rate. Now, so but prior to using this K as erodibility, we need to verify relationship of K and so there is another relationship of K, which is inversely proportional to the uniaxial compressive strength of a material. So based on that, so based on that, I first tried to verify my determined K with this equation, and if plotted the, I mean, the try to understand the relationship between KSN and K. Now, here are the results. So here we see that the most of the nick points within the river lies on the harder rock or the hinterland part of the MCT, and we all know that MCT separates the higher Himalayan crystalline from the lesser Himalayan rocks. So here we see that the most of the nick points are restricted within the harder, less erodible rocks, whereas in the Rangit window region here we see very few nick points. And from my previous first objective, active zone. So this can be explained by this diagram here. So if a rock is coming from a softer rock to harder rock, in that case we see very uh, I mean gentle, sorry, gentle steepness downstream. But in the reverse case, what we see that the softer rock will erode fast and we will see a steep segment in the downstream direction. Now, if you look at the hypsometric curves also, here we see that the basins which lies on the higher Himalayan crystalline or which consist of higher Himalayan crystalline rocks like this part here are showing convex curve, but the Rangit window basin here is showing a concave curve, and rest of the basins are showing convex curve. So from this also we can see that the rock type has a major role to play. So first, as I already mentioned, so first I tried to understand the relationship between K and UCS, and here we see that the our relationship follows. And then we moved further and tried to understand the relationship between KSN or the steepness index with the erodibility, and we see a inverse relationship here as predicted by this equation here. Now, moving forward, I try to understand the effect of erodibility with the steepness and as well as with the river long profile. So here are the river long profile for all the 11 subbasins. Now I'm going to discuss about only one subbasin here. So here we see within a uh, invariable zone of erodibility, we see the red curve indicates erodibility, the purple curve indicates the steepness index, and the black curve indicates the river long profile. So in this zone, we see there are several anomalous steepness within the river channel. So upon verification with respect to the satellite imagery, what I observed that this is due to the large scale landslide within the river channel. Now, when we encounter the Ramgarh thrust, as I already mentioned, that this here starts the lesser Himalayan, sorry, the Gondwana and the rocks here. So here we see the erodibility increases. That means the rocks are softer in this region. Here we see, firstly, the steepness decreases. Then again here the erodibility increases. Again the softness of the rock increases, and then it drops. And when it drops, there is a spike in the uh, mm, uh, uh, river steepness. So this can be explained by if a area is uplifting only then. So we all know in a uplifting region there is the down cutting is I mean the river down cutting is dominant compared to the bank erosion. So in that case, we should observe a steeper segment, but here we see a less steeper segment because in that case, here as the erodibility increases and the rock is uplifting, that's why the relief is less or the steepness is less in this region. But steepness is less, and from this, what we can see say that as so here we can see that the hardness of the rock decreases, but the steepness also decreases. This is because the area is currently uplifting, and in an uplifting channel, so in a transient state of a river, when there is not in, there is no equilibrium between the rate of uplift and rate of erosion. In that case, we can see in this type of structures or this type of pattern within the river steepness. Now, I have tested this new morphometric indices in several other places. One in the Mandakini River Basin, which also lies within the Himalayan region, and another one is the Penna River Basin, which is situated in the southern Indian part, and it is situated within a stable area. So here we see for active areas, it is showing inverse relationship, but for a stable area, it is showing positive relationship because as the erodibility increases, the steepness also increases because there is more and the down cutting is more effective on the softer rocks. Now, from this study, what we can conclude that this bedrock erodibility coefficient controls the behavior of the morphometric indices, and without considering the bedrock erodibility, the morphometric indices should not be interpreted. And then the bedrock strength has direct control over the river long profile, and low strength rocks in the lesser Himalayan duplex region erode faster, and the area has lost its taper at a faster rate, shifting the deformation from the hinterland side towards the from the foreland side towards the hinterland side, or the outer sequence deformation here. So this work also published recently published in International Journal of Earth Sciences. Now, let's move into the objective number 3, which is understanding the kinematic history of the development of LHD by sandbox analog modeling. So this is a typical example of the sandbox model and the experimental setup, and we try to simulate this the balance cross section given by Bhattacharya et al. So for our experiment, this is the experimental setup, initial setup. Here we introduce a glass bead layer which acted as a Gondwana cold shell layers, and we introduced a proto wedge of 15° and a basal angle of 15°. So we performed several experiments. So at first, there is no complexity within the system, only glass bead layer. Then gradually we introduced complexity within the system at first by introducing 5° basal angle, then changing the base material from paper to sandpaper to increase high frictional to simulate high frictional basal decolma layer. Then we introduce proto wedge within the system. Then we optimize the proto wedge thickness to get our desired result. Then we introduced erosion and sedimentation within the system, and then we optimized the rate of erosion and sedimentation. So in this erosion and sedimentation experiments, what I did after initial 20 centimeter shortening, erosion is introduced, and the erosion is performed for every 5 centimeter of shortening to maintain a constant taper angle of 15°. Now, so there are some examples of experiments, but the interesting thing is that here for the intermediate glass bead layer, we see that thrust sheets are propagating further compared to the other experimental setup. And finally, what I got that this kind of structure. So here I was able to simulate the duplex structure. So the glass bead acted as a roof thrust, and there is overthrust as well as underthrusting here. But the limitation of the model is, so here you can see from these two diagram that our duplex structure formed near the backstop, whereas in real scenario it is way towards the southern direction. So this part needs to be properly done, and I couldn't complete these experiments because of some unfortunate incident in the lab, and I plan to do it later. I'm trying to optimize the position and changing several other parameters. I will try to get the desired result. Now, so from this, what the basic idea what we got is that there was a high uh, the required parameters for a duplex formation is a high frictional basal layer with a intermediate low strength layer. Then there should be an initial proto wedge, which will restrict the thrust propagation, and then a low dipping basal layer, and erosion and sedimentation. The sediments were carried farther away from the zone of deformation. So here, as I mentioned here, so in this experiment, I eroded and the erosion and sedimentation rate is same. I mean, the same eroded volume is deposited here. But if I deposit and if there is the rate of erosion is higher compared to sedimentation, in that case, this structure it gives a favorable conditions for formation of the duplex structures. Now, Then fourth objective was to understand the effect of active tectonics on landslide occurrence in FEMR techniques. So in my first objective, I mentioned that most of the landslide that we found are because of the tectonism. So that dynamic interplay between the uplift and erosion makes the slope vulnerable, and any triggering mechanism like rainfall or earthquake can trigger landslides within the system. That's why I tried. So here the landslides and tectonism is related, and that's why I tried to understand the effect of landslides. The effects of tectonics on landslide. So the first objective was to determine the potential failure plane using FEMR technique, and if possible, to propose a landslide early warning system using this same technique. So the basic hypothesis is here. So if the area is actively down cutting, in that case, we will see steeper river bank, and a steep river bank will form some unstable material condition, and due to the gravity this material may fail, or these slopes may fail either due to gravity or by introduction of water within the system during the monsoons. And I used the same instrument and took vertical measurements along the landslide plains, as you can see from this conceptual diagram here. And this is the typical EMR profile of a landslide surface. And now, in our earlier study, we established the relationship between maximum FEM amplitude with the shear stress for the Himalayan rocks. So, from using this equation, I calculated the shear stress. So here, and using this, I calculated the normal stress on the failure planes. And these are some example of the EMR profiling. And I also numerically simulated the slope failures to know the potential slope planes and to calculate the stresses on those planes using these values here. And these are the these are the slopes that I have studied for the region. So there are some few examples from the slope failure simulations, and we can see the slope failure is at several levels. It's not a continuous single plane. So the failure can occur from several levels here, and this complex plane here. And then I plotted the shear stress and the normal stress within a mode coulomb space. Here we see that the stresses which shows less than 1 bar normal pressure, no, sorry, normal stress, are responsible for shallow landslide, whereas if the normal stress on the failure plane is greater than 2 bar, it generates very deep seated landslides. And here we see the most of the sandstone slopes are very pretty vulnerable for failure. And although this landslide, which shows more than 2 bar of normal pressure, can trigger deep-seated landslide, this can also trigger shallow landslide by introduction of water within the system, as we all know from the Moore Coulomb diagram. So by introducing water, the more circle shifts toward the left, closer to the failure envelope. Now, then I compared my result with the national landslide susceptibility map here. So by comparing the susceptibility from NLSM and my study, what I see that the most of the data are in good agreement with the national susceptibility map, and based on these two, I then finally propose several vulnerable slopes. And here we see there are the slopes marked, which are the vulnerable. The most vulnerable one is marked by red color here. Now, here is the here is the verification of the data. So this column indicates the scenario during the field work, then the slope recovered, and then again failure is triggered within those slopes. So from this study, what we can conclude that the FEMR emission phenomena is independent of rock type, but the critical FEMR value for failure is dependent on the rock type. Why? Because you see that the most of the sandstone slopes are showing very low stress values, whereas for the phyllite slope, the range varies quite largely. And then the critical value of the FEMR pulse depends on the bulk modulus and uniaxial compressive strain of the rock, because the harder the bond strain, the more energy will require to break it. And so this manuscript is submitted in the journal Landslides, and which is under review currently. Then moving forward, the fifth objective was to understand the effect of active tectonics on reservoir triggered seismicity and its comparison with Koena. So why I'm talking about Koena? So in our parallel site study, what I studied that, so based on the simple Moore-Coulomb envelope and failure criteria, so I hypothesized that the reservoir is built upon on top of a fault zone, and that's why the fluid percolated within the region, giving giving rise to the movement along the faults. And here we see that without introduction of the fluid overpressure or the effect of this reservoir, just only considering normal hydrostatic gradient, stress gradient, in that case, we see at that up to several 10,000 meter depth, which is the maximum seismogenic depth for RTS, reservoir trigger seismicity. We see that the most of the fault planes are already critically stressed, and this criticality comes from the collision between India and Eurasia. So here we see that the fault planes are mostly strike slip, and it is at a high angle with the stress direction, and this is favorable for fault movement, strike fault movement here. So the Himalayan orogeny is actually responsible for uh, seismicity in the Koina region, and the introduction of the reservoir on top of the faults just triggers the seismicity, triggers the faults which are already in critical state. Now, so, but in Himalaya, so basically the question arises: so if the Himalaya is the actively deforming zone, why don't we see any kind of reservoir-triggered seismicity within the Himalayan region? So to do that, so I chose the Tista Lower Dam. Here we see that the dam is built on the fault plane, more or less, and very close to the fault plane, and there is a high possibility to water percolation through these fault zones, if it is a conduit fault, obviously. So to understand the fluid pressure development, I use the 1D poroelastic diffusion equation. So it is a, here we couple the effect of couple the sorry. So why I say poroelasticity? By poroelasticity I mean that as we go a deeper part, the pores or the void spaces due to the surrounding stress become smaller, and eventually some pores get closed. So this equation actually combines the effect of permeability as well as the pore size by the using the diffusivity constant, where the diffusivity constant is determined by using the permeability, porosity, and the total compressibility and the dynamic viscosity of water. So here the model parameter was the pore pressure diffusion. So what I wanted to study is the pore pressure diffusion along a 1D fault up to 5,000 meter depth. Then the reservoir water level is varied to check the maximum permissible limit of the dam construction. Then how the fault plane orientation affects this seismicity. This is also studied. And then as I mentioned, that I have chosen both barrier fault as well as conduit fault, and this is differentiated by different permeability values here. So these are the input variables and the values of the input variables that I've used. Now, if we talk about the result, so for all the reservoir heights, which varies from 25 meter to 100 meter here, so we see that the maximum pore pressure near the surface varies, but for 10 within a 10-year period of time, the pore pressure reaches steady state, more or less steady state. Here is, as you can see, it is very close to the steady state nature. And due to the and we see that at the bottom near the 5 kilometer depth, the pore pressure is almost zero. This is because of due to, as I already mentioned, due to the stress, surrounding stress, the pores get closed and there is the permeability reduces. And but for a conduit fault, what we see, sorry, for a barrier fault, what we see this that the water can percolate up to only 150 meter, because already the fault has very low permeability, and then the poroelastic effect elasticity comes into effect, and the pores get closed. So the permeability of a already low permeable fault decreases. So from this, what we can say, the barrier fault can never trigger seismicity. Now, if you look at the stress distribution with depth, what we see that this is the variation of shear stress for different reservoir depth here, and this is for 30-degree fault plane, and this is for 45-degree fault plane. And in terms of slip tendency for 45 and 30-degree fault plane, we see that if the reservoir load is low or the reservoir height is low, in that case we see that the fault is more, I mean, moderately, the slip tendency is more moderate. But as we increase reservoir load, we see that the slip tendency reduces and almost becomes zero, near zero. So why it is so? Because the Himalayan region lies on a compressive zone. So here the horizontal stress is maximum, and by introducing vertical load within the system, what we are doing, we are reducing the stress anisotropy, thus increasing the stability of the area. So unlike Koena, here we reservoir construction actually increases the stability of the region because it is a thrust fault. But in Koena, it is a strike slip fault. That's why it is already stressed because of the uh, I mean India Eurasia collision, and the impoundment of the reservoir triggers the seismicity. Here from the motorcycle also we can see up to here, both the motorcycle shows up to 10-kilometer depth of, and here I am choosing the maximum water levels, but still we see very low slip tendency. But for Koena region at 10,000-meter depth, using only hydrostatic gradient, we see the fault planes are already critically stressed here. Now, so from this, what we can conclude that stress regime plays an important role in controlling the reservoir triggered seismicity. And as I mentioned, unlike the Koena-Warner region, which is dominated by normal and strike slip fault, Himalayan region is dominated by thrust faults, and thus the impoundment of reservoir increases the stability. And compression parallel strike slip faults, as I also mentioned, so these are optimum for reactivation, as we can see in the for Koena region here. Now, okay, and then the Himalayas increasing water load due to the reservoir impoundment increases. Is already thing I've already mentioned. Uh, and yeah, another thing is deformation is possible near the surface level, which is accommodated by the vertical compression. As you can see that the near the surface, the slip tendency is high here. So the last objective is to give a overall summary of the, I mean, the different kinematic evolution history of the study area. So firstly, the high frictional Indian plate and low angle subduction beneath the Eurasian plate gave rise to the Himalayan mountain belt. So from our study, what this we understood. Then after around 10 million years, so erosion introduced by, as the monsoon happened in the region, monsoon started within the Himalayan mountain belt, and erosion is introduced. Because of this erosion and reduced taper angle, out of sequence thrust generated, and the Gondwana cold shell layer acted as an intermediate low frictional layer, which gave rise to the duplex within the area. And due to the formation of the duplex, the uplift also increases. And due to this high uplift, the erosion also increased within the area. So the rivers became in transient state, shifted from steady state to transient state, and that high down cutting is also observed. And due to this high down cutting, unstable slope generated, which are susceptible to erosion, and then it triggers landslides. So this process is this interplay between the uplift and erosion is mainly responsible for the duplex formation as well as the current present day uplift near the Rangit window. And uh, okay, yeah. And this collision actually gave rise to the reservoir triggered seismicity in the Koena-Warner region. So this is all about, I mean, this is the summary of my thesis, PhD thesis here. So yeah, thank you. Yes,
Thank you, Deep. Now I open this forum for questions and answers.
yeah, of course.
Well, Jyotima, may I ask a question?
Yes, please go ahead, sir.
Deep,
Hmm.
uh,
Yes, sir.
thank you for a nice presentation, and you are doing good work. I'm very happy to see this.
Thank you, sir.
I have only a few queries.
Yeah,
One
yeah.
is that, as I see here, that you have plotted many of the. First, we come to the geomorphic indices. You have
Okay.
plotted a number of long profile,
Yes.
and you have identified some nick points as a slope break.
Yes,
Okay.
sir.
Now, my point is, it is well known that the nick points actually migrate
Yeah.
upslope, up dip
Yes.
of the river. So
Yes.
the points at which you are now finding the slope breaks, and
Yes.
where you are supposedly correlating them with the thrust bound different rock types,
Hmm.
it may not be actually the position where the nick points were generated.
Yeah.
So have you
Yeah.
taken that into consideration?
Yeah, so for this study, I didn't consider that because yeah, I know that the dig point migrates,
And
but
they have a certain velocity of migration, which is mathematically defined.
yes, yes, yes. So we have some mathematically defined nick point migration velocity. Here I didn't consider that because I mean what we mostly see in the this kind of studies that people generally use this present day setup for identifying the zone of active tectonics. And here, as I've seen very good correlation with the just a thrust boundary. Here we see a nick point also. In that case, that's why I didn't consider the nick point velocity, because yeah, we are getting very good correlation within the fault and nick point itself.
Okay. Another point is that you have, of course, this is a very short presentation. Everything cannot be understood from this. But
Yes,
as I see that you have not really mentioned the nick points are generated. You have mostly correlated them with the erodibility of the rock. Fine.
yes,
That is
yes,
of course one parameter. But at the same time, what is the change in the total flow in the river? I mean, if there is a tributary meeting the particular river, which order river you are talking about, all these parameters are also important along with erodibility of the rock, because
yes,
the
sir, yes, sir.
same kind of erodibility
Mhm,
variation which is generating a particular slope break
mhm.
will be is very much susceptible to changes if there is either a big tributary joining, or there is
Yes,
a seasonal, very heavy seasonal variation in rainfall, like
yes,
say extreme events and things.
yes, sir.
Okay.
So sir, as I forgot to mention, so for this particular nick point, I mean steepness, high steepness area here. So upon verification, what I observed that this is because of the tributary is joining with the Rangit River, and that's why the combined effect of the, so the drainage is I mean drainage rate is very high there, discharge rate, and that's why there is a nick point here also, high steep area. Yes, of course
So that
the
is, so that is in addition to the nick points that is caused by the erodibility of the rocks. That is what you
yes, sir. Yes, sir. So yeah. So if we look at the, so for this particular section here, we see the same type of erodibility.
are. Mm.
So in that case, if I am seeing any variation in steepness, then I move to the satellite imagery and verified this. So for the very northern part, we see that there are several landslides within the river. That's why we are seeing this, as well as when a tributary joins with the main the trunk stream. In that case also, we are seeing this kind of patterns. But if I
Just a minute. The pure purple curve that you are now following, is this is indicating the slope or what?
what's the
That particular purple color curve that you are now following, it is
yeah,
indicative of slope or what? What did you mean?
steepness, yeah,
Steepness.
steepness, yeah.
Steepness. Okay.
Mm,
So then we just as a consequence of your that earlier question,
mm,
in the right hand side where you are having a high erodibility rock, possibly Gondwanas. So
mhm.
here suddenly there is a spike of upward spike of a very steep slope, and then suddenly
This
a
one,
negative spike. What is the explanation of that? Yeah, that
this
one.
one, sir.
Yes, yes, yes.
Okay, so here we see that the erodibility decreased. So that means the rock strength increased here.
Hmm.
So the and so that means the rock is coming from a low erodible rock to high, sorry, a highly erodible rock to low erodible rock. In that case, we should see, I mean, if I look at this diagram here, so this is the scenario there. from a soft rock to hard rock. In that case, we see a downstream direction. In the downstream direction, sorry, in the upstream of the hard rock, we'll see a steep segment within the steep segment within the river channel. So here also, I mean, yeah. So the area is more or less similar here. So I mean, yeah, I mean the distance between these two boundaries. So here it might be possible that because of the mapping, because the here we see the very less distance. So it might be because of mapping error. Because if I could correctly mark the boundary, in that case, with the histological boundary, in that case, this might. I mean, if we look at here is sharp increase in erodibility in softer rock and then sharp increase in steepness. So this is maybe because of the error in mapping, because this should be within this region when the erodibility suddenly increased, as because the river is coming, sorry. So this will indicate this scenario here. So this is might be because of the mapping error.
Okay.
My here.
Okay, my last question.
Yes,
Last question is that from the if you advance your slides in the experimental, physical experimental part,
mm,
yeah, here you are showing a duplex in the lesser Himalayan, which actually simulates the lesser Himalayan duplex. Yes, in this figure.
mm,
So my question is, a lesser Himalayan duplex or any kind of duplex in this sense,
mm.
do you mean to say that from your experiment it seems that it is always in a advanced stage of orogeny? That means a proto-age has already formed. So how can you explain a proto-wedge? If it is an orogenic wedge, then 15-degree proto-wedge means it is a considerable amount of horizontal shortening, which has already taken place, and then the duplex is developing. Is that the case? But
Sir,
that
can you
is
please?
the hinterland
Can,
of an origin.
okay, sir. Can you please repeat the last part of your question, because the network.
I am asking that this duplex has formed in a model where you have given a 15-degree proto-wedge.
What?
Is that correct?
Yeah,
So how do you explain this in a natural situation where a proto-wedge means if it is an orogenic wedge, then it has been already subjected to a lot of orogenic shortening, and then suddenly the duplex is developing, or the duplex actually develops right at the onset of the orogeny? That is my question.
okay, okay, sir. So the rationale behind choosing this proto wedge is like, suppose if we consider the look at the geometry of a accretionary prism, in that case, so the within a subducting plate and the overriding plate, in that case, if we look at the, I mean, sedimentary sequence, in that case, it
No,
actually looks like kind of a.
you have not understood the question. What Professor Chattopadhyay is asking, can you actually make this antiformal stack or duplex without the presence of the proto wedge? If you
Yes,
don't
that is
have the proto
yes,
wedge, can you
yes,
make that?
Okay,
yes, yes. That is my question. I mean,
The
is
answer is
proto
no.
wedge essential for
no,
a
no,
Yes,
development
the
of a
answer is
duplex?
no. No, you need to have the proto wedge.
yes, yes. Yeah, we also tried with, as I mentioned here, we also tried with this simpler setting. Here we didn't get any duplex structure. We need the proto wedge. We needed the proto wedge for developing this duplex actually.
But
Without the
the classical duplex models do not consider any development of a pre-existing proto-wedge, isn't it?
yeah.
So why this mechanical constraint? Do you have any explanation for that?
Yeah, so because so what I observed during the experiments, that if I don't put any proto wedge, so this kind of structure will actually form. So there will be the thrust will glide over the low frictional layer and it will progressively move forward. But to restrict the formation and to separate the overthrusting and the underthrusting, what I observed that a proto wedge is needed just to, I mean. To just to separate the deformations, and yeah, what was that?
But my question is the deformation could have been very well differentiated between the top layer and the ground layer. I mean, as you are mentioning, you are correct. So in that case, the glass bead is actually a break, no? I mean,
Yes,
the upper layer and the lower layers are decoupled by the glass bead
yes,
layer. So why this is, you are correct. I also during my PhD days in 1990s, I tried a lot trying to produce the duplex structures as mentioned in the classical, the Feinhofen duplex and all these things that people have described from all over the world. You are very much correct that with a normal sequence, even with a low velocity or low strength layer, a duplex structure is not easily produced. But my question is there any solid mechanical explanation of why it doesn't? I don't know. Actually, to me, it's
Okay.
still a bit of an enigma.
Okay. Just a second.
Because you are doing modeling on this, I have left this many years back. So because you are doing modeling on that, please think on that line.
Yeah, you
Yes, sir.
should think about it, Deep. I think it's.
Yes, sir. Yes, sir. Of course.
Uh,
Thank you, sir.
Anupam,
Okay, fine. Yes, sir.
the question that you have put, can it be that the mechanism of deformation in your model, it is primarily by granular flow, whereas in nature, the formation of the thrusts and the formation of the duplate is not by granular flow, it is by different mechanism of deformation. So could it be the difference, could it be because of the two different mechanisms of deformation?
Yes, sir. That is what I was just asking, because you know very well, sir. You have visited those areas, the Feinhofen duplex and the duplexes related to the Moyen, basal part of the Moyen thrust zone. There nowhere there is a very thick, wedge kind of thing anywhere.
I have some doubts about how far these sandbox models would apply to the actual duplay in the field. I have some doubts about that. Because the other difference that in this case is that the duplay is forming towards the backside.
Yes, sir. That is absolutely true.
And actual duplay is that we are observing is not towards the backside.
Yes.
So whether the parameters of the experimental model, how far they are applicable to the
one explanation of that comes to my mind is that in that case, if the last in the natural case, I mean, if I refer to the lesser Himalayan duplex, maybe the thrust tag which is actually behind this duplex is actually working, acting as a pushing plate in that particular case. Then it can be actually apparently in the frontal part, but basically the hinterland part is actually working as a indenter in that case. That is possible because they are metamorphic rocks and they may be hard rocks and all these things.
Yeah, sir. Right now, I remembered why we introduced proto-wedge within the system. So without proto-wedge, what we were observing, as I mentioned earlier, like this, the thrust it was gliding over that. But since the duplex there is showing also the foreland dipping structure as well as hinterland dipping structure. So to restrict the upward propagation of the thrust sheets, so I introduced this large mass by introducing proto-wedge within the system, so that this kind of this bending can be possible, because when we
that
try.
is fine, Deep. That is fine. That is because you have made trial and error, and this is the way you could find a duplex. That is fine. But what we are discussing and what Sir is presenting is that what happens in nature actually.
This proto-wedge, how could it form in the actual Himalayas, the formation of the proto-wedge before the formation of the duplay? Do you think that's a very realistic model for the Himalayas?
Yeah. So yes. So the thing is, I need to perform and study a lot on this subject actually. So this was actually trial and error. And what I thought, the primary consideration was within the accretionary prism, and we see that there's a triangular section. If I consider, so I just wanted to simulate that part by the proto-wedge. Then with subduction. So yes, it was actually a trial and error firstly, and there are some other literatures also.
You produced a model which gave rise to a duplex structure.
Yes.
That is okay. That is fine. but how far are the boundary conditions of your model applicable to the Himalayan situation?
Yes, sir. Yeah, that I need to, I mean, study more
Because
here.
then you must have some sort of mechanism which gave rise to that proto-wave before the formation of the Himalayan duplex, and what produced that proto-wave in the Himalayas.
Yeah. Yes,
Deep,
sir.
I have a small question.
Yeah, yes, sir.
The stress method of stress determination that you followed, that measures only the surface stress. Am I
Yes,
correct?
sir. Oh, yes, sir. Near surface stress.
Near surface stress, but the surface stress is very susceptible to the topography.
Yes.
So, how far is your variation of stress, and whether it is really the regional stress at the depth of the fault or at the seismogenic depth?
No, no, sir. No, sir. It is not this regional stress because, uh,
So, if this is
here,
only a surface stress, then it
yes.
will be have relevance for landslides. But do you think it would be have any relevance for the movement on the faults at a depth of say 10 kilometers?
No, 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 sir. So the thing is, so here the thrusts, the stress direction that I show by blue color, these are the regional stress, and these are measured from very deep earthquakes. So this is the actual stress orientation that are responsible for the fault movement.
No,
But we,
these blue lines. Did you
yeah,
get them from the literature or you calculated them?
no, I've taken from the wall stress map.
That is perhaps also partly derived from the GPS measurements.
Yes, sir. There are several tools, some from GPS, some from earthquakes, and some also from borehole breakout data.
Approximately the average direction of stress in the Indian plate is, especially in the Himalayan region, is north 23° east. You are getting from north 7 to north 20 or something,
Yes,
that range you are mentioning. So that broadly matches, but maybe there is some local variation that is quite possible.
As in local variation may be entirely due to topography itself.
Yes.
Sir, he's just let me just come in here. He's not. I mean, the stresses that he is measuring by FEMR technique is not responsible for the deeper fault movement. As you have correctly indicated, they are near surface stresses. They are susceptible to the topography and they are influencing landslides.
Yeah.
yes,
So
yes,
yeah, that's how they are. The only thing what he's trying to actually emphasize is that the areas where the areas which are actively deforming, that is where you see a surface stress realignment. No? So that is an effect of the active tectonism. So if an area is actively deforming, you will see the realignment of the surface stress parallel to the thrust.
Deep, another question.
yes, sir.
You mentioned something about the balance between the uplift and the erodibility,
Yes.
in connection with your long profile of the rivers.
Hmm.
So, are they at equilibrium? Have they reached an equilibrium stage, or is it?
No, sir. It's in transient state.
It's in a transient state.
Yes.
Sir, are you speaking? We can't hear you actually.
No, Deep answered. I had a question. Deep answered that.
Okay, sir.
I asked whether the river profile has it reached an equilibrium stage
No,
or is in a transient state.
it's in a
No, sir. Transient state.
Yeah. Okay. Trideep, please go ahead.
Deep, thank you.
Yes,
Very nice work and a relatively new one.
thank you, sir.
Uh, I just have one query that is related to the sleep tendency. You have measured many sleep tendency analysis in the
Hmm.
Himalayan region and Koina also. So as we know that it's a ratio between shear stress and normal stress,
Hmm.
resolved shear stress and normal
Hmm.
stress. So how have you measured that normal stress and shear stress, or I would say the quantified? That is solely based on FEMR, or have you used any other technique?
No, no, sir. Actually, so the here the stresses that I measured. So it is not the actual stress. I mean, from FEMR we can't measure stress. I mean, for this case also only. So we can measure only the SH max azimuth. But what I did here, so here I use this equation as you all know. So what I did that we chose a unit value. I mean, the as it is a ratio. So what I chose, suppose the sigma 1 and sigma 3. So I chose some values for that, and I based on the how the angular relationship is affecting that. Based on that, I based on the angle between the thrust and the stress orientation, I calculated the stresses. So at the yes, the initial stress was not the actual stress there. So there I considered some hypothetical values there, because for the whole area, so sigma 1 and sigma 3 here, and then try to understand the ratio. I mean how they are acting.
So actually, that was my question. So how what was the basis of that hypothetical value? I mean, you have assumed something, right?
Yes, and another thing. Oh, sorry. Yes, sir. So the thing is, I took some values from a Mark Jovak paper. So
So,
what he did, he for the wall stress map, he, I mean, proposed some stress values for several regions, and as well as
No,
he,
here, Deep, you have the stress. So here, Trideep, here the stress sleep tendencies is the sensitivity, how the sleep tendency changes with respect to the mutual uh, directional relationship between the local stress as well as the thrust strike. That is what is being shown here. Yeah, with respect to the stress values, the values are used here in another paper where we have calculated using FEMR only. We have calculated the value of stresses in a tunnel, okay, in that area. So
okay,
such values are actually used for normal stress and sigma 1, sigma 2, and sigma 3.
okay. Thank you.
Deep, I have one small query. Acha, Sumitra da is asking some question. Please let him first.
Sir,
Sumitra, please.
Sumit sir, please go ahead.
Uh, 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 Thank you. I have a small question, may
yes,
not
sir.
be directly related to your research. Why do the duplet zones laterally die out? If we see the entire length, strike length of the Himalayas from, say, from your area, the Darjeeling, Sikkim Himalayas to the Arunachal Himalayas, a very small part of this stretch has these duplex structures, and that too for a very small lateral extent.
Yes, yes,
So everywhere the duplex die out within a small distance. Do you have any
yes.
idea, or does your work throw any idea about why it laterally terminates and why it is laterally restricted to such small areas in the entire orogenic belt? May not be directly related to your research, but it was
Yes, yes,
question
yes, sir.
I
It's actually
came to my
a very
mind.
good question. And yes, yes, sir. For my research, I didn't consider that factor, and so that's why I don't know much about that. Secondly, that my sandbox model part was not completed actually. So there was a fire incident. I had to stop the experiments in the, I mean, midway. So I didn't actually still don't have all the knowledge regarding the modeling. So I and yes, and this part I don't know. Actually, I don't know the real answer why it is so.
Okay, okay, okay. Thank you. Thank you.
Okay, I think Jyotirmay has also raised his hand. Another Jyotirmay.
Yeah. Hi. Can you hear me?
Yeah, yeah.
Yes.
Yeah. So thanks for this presentation. I have a small query or curious. I'm not a field geologist, so I do not understand all these measurements. So it's a kind of the question that Tridip has already asked. Like, how do you measure the stresses? Because when I saw your plots in this reservoir for Koyana and somewhere near the in
Darjeeling.
the Sikkim part, I think you were giving a depth variation of the stresses.
Hmm. No, no, no,
Uh,
no, no, no. So, oh yes, so for this, the stress
uh,
direction, this I considered from a stress ratio of 1.0. So, SH by SV equals to 1.08. So, this is from a borehole breakout data near Assam basin. So, I didn't get any in situ data for Sikkim, Darjeeling, Sikkim area. So, I chose the data from the Assam region.
Okay, I think there was so that is a slide after you this diffusion equations. The next slide, yeah, next slide.
Hmm.
I think. Oh no, maybe the next one.
This one.
Yes, this one. So here I see like there is a depth variation of the stresses, and
Hmm.
I see like your stress is going beyond like 100 megapascal, close to 150 megapascal at around 4 to 5 kilometer depth. So I was just curious, like, how do you get this huge amount of stress at this depth?
Yeah, so I from that paper, I mean I got the sigma 1, sigma 2 by these values, and by using the Moore Coulomb equation and those equations, I calculated the shear stress and normal stress.
Yeah, but do you think this is really possible to get like 100 megapascal or at 4 kilometer or 5 kilometer depth? Like, I don't know. I mean, how these stresses are calculated at Himalayas, but yeah, this looks bit higher on the side. But yeah, maybe some other
Yes,
expression that I don't know.
yeah, yeah. So I don't know exactly, but the thing is, in several, so there is a paper from Tien Gog and Mark Zobak. So there they mathematically actually calculated this kind of stress, I mean the stress gradient, and with numerical modeling also. So by considering that those, if I consider that those papers, in that case, this is possible. But yeah, near it is only possible near the orogenic belts only. So yeah, all the
Okay.
stress values, whatever I collected from those paper only.
Okay. Yeah. Thank you. I had this question only.
Okay. The next question there is, I think, in chat box we have one question from Aditya Ray. Thank
Uh,
you for.
Excuse me, can you please excuse me for a second? I need to go to the washroom, just for a second.
Yeah, yeah. Go ahead quickly. Come back.
Thank you, thank you,
Everyone
thank
is
you, thank you.
waiting.
Yes, 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 yes. Thank you, thank you, thank you.
Sorry for the interruption. The speaker had to use the washroom. This is for the first time that happened.
He has drank too much of water.
Yeah. So we will now onwards we will also kind of entertain presentations from
Hello.
senior PhD students, so that when they expose their work to the expert panel, like something like here, the feedback only improves their work. So if you have a nomination, please let me know. We can organize students talk as well. Okay, so the next question from Aditya. Thank you for your presentation. My question may be a bit unrelated to the topic, but does excessive groundwater extraction, I think abstraction, from confined aquifers in the region increase the susceptibility to landslides?
Yeah. But yeah, this can happen, and this can also be seen in some northwestern India part. So there is actually, for that landslides to happen, we need steep slope or high slope. In the northwestern part of India, we see groundwater subsidence as well as some natural collapse of the ground surface. So in the mountain area, yes, this can happen because as we extract groundwater, the ground might subside, and this can lead to a landslide in the region.
Okay, there is two questions from Anne. You mentioned that the thrust propagation in your models is not directly matching with the nature. As we know, the topography of the wedge plays a crucial role on the propagation in sandbox models. So my question is that the erosion rate introduced in the model, is it properly scaled with natural data or just introduced in order to keep a stable taper angle?
No, so it's not scaled to the natural data because we don't know the. I mean the throughout the. I mean the this time scale, this long time scale, we don't know the erosion rate for that. So this is just to keep the taper constant. Yeah. So this is not scaled with natural erosion rate, long term erosion rate.
There is another question. Have you tried to change the analog material of your decolma and see the effect?
No, we only used glass beads.
No, you also used sandpaper to create high.
Oh, so yeah, for the basal decolma, I used sandpaper of different grit sizes, but for the intermediate decolma, I didn't use any other material, only glass beads. Like some people use mica layer and all those, but I didn't use any of the only my glass beads.
Okay. Any further question?
I have one query, if you allow
Yes,
the
sir.
response.
Yes, Anupamda, please go ahead.
I just wanted to know that from your landslide susceptibility, I mean the slope vulnerability study that you have mentioned, that you have seen the EMR signals and things, have you considered the slopes as only the slopes, or you have considered the anisotropy of the different rock types which are occupying the slopes?
No, sir, only the slope geometry.
Because you see the anisotropy will play a big role if you have a schist or a slate
Yes, sir.
occupying, and those areas are very vulnerable. In fact, just as a casual observation, if you go to the Himalayas, you will see that immediately after the rainy season, when
Yes.
things try to start drying up with
Yes.
sun coming out, then maximum landslides occur. And that is because of the expansion or contraction of the water vapor, or in vaporized state or whatever, in fluid state, the water volume contraction or expansion in the jointed planes of
Yes.
highly joint planes, not only the tectonic joints, but also the fissile planes of slates and schists. That has been
Yes.
pointed out by many people. So only seeing the slope as a slope geometry will be an oversimplification. You see,
Yes.
of course,
Yes, sir. So
when you model, you have to do some simplification. I agree with that. You
Yes.
cannot take all the complicating parameters into one mathematical model. It is not possible. But please think about these aberrations.
Yes, sir. So we were aware about these factors. So our main goal was to propose a systems which can identify this susceptibility in a relatively quicker manner. So all the existing early warning system, I mean, there are several kind of early warning system existing. So those take much more time. So our primary goal was to eliminate those complexities. Yeah, I know in for I mean to be a practical, I mean, so that anyone can handle and operate this part. So that's was the main motivation. That's why we kept our study quite simplistic. Yeah.
And that is fine. That's fine.
Jyotirmoy, can I make just one comment, not a question?
Yes, sir. Please go ahead.
Yes, my comment is in
Yes,
the
sir.
classical critical taper model, the taper is created by the thrusts, by
Yes.
the Duplé type thrusts. Whereas you have already produced a taper before the Duplé formed. So
Hmm.
the Duplay is modifying an already existing taper.
Yes.
So I think so when you apply the change of the taper angle from the classical model to your model, I think these are not directly comparable. Because
Yes.
in the classical critical taper model, the critical taper is caused by the thrusting itself,
Yes. Yes.
not that they have a pre-existing wedge.
Yes.
Sir,
Ye-
just to add to that point, we also tried to go into that, tried to model,
Yes,
so that the tape actually this wage actually develops by the experiment itself, and then whether the under thrusting and duplexing happens. But somehow that doesn't happen. Uh, Whatever experiments, I mean, we tried several such experiments, although some authors have demonstrated some numerical models to explain such things, that the taper actually develops by the experiment itself, and then the duplex happen as a product of under thrusting underneath it. But we could not create it, I mean, after several experiments. So don't know why.
you may try numerical modeling.
Yeah, perhaps that is the way, perhaps analog modeling is not going to give us the complete picture. True.
No, even in numerical modeling, you have to assume many things
Yeah.
which may not be
Yes.
exactly fit
Yeah.
to nature. So always there will be some assumption, any kind of modeling. That is the problem.
Yes, sir. Dilip Mukhopadhyay, sir, please go ahead.
Uh, there's already been quite a bit of discussions on this. I would like to make a comment for Deep Das personally.
Yes, sir.
Is that your many of your slides, there are too much of information for your audience to digest in a flashing by mode. I have my screen. I can use my two fingers to enlarge and shorten. But even then, by the time I enlarge it and try to read your diagram, you have already gone to the next slide. So I'll have to get back and do that. So it may not be, you are young, I know. You don't have as much experience as I have, uh, rightly or wrongly. That putting too much of information in a single slide can be detrimental to your talk, because you have to, after all, you have to keep the attention of your audience.
Yes,
So
sir.
please do not put too much of information in your slide, in a single slide. You can do
Yes.
that because you have 1 hour time, so you can do
Yes, sir.
that.
Thank you, sir.
This is
This
just a
is, yeah.
suggestion. This is
Yeah,
just a
it's actually a good suggestion. But to be honest,
suggestion.
I plan to, I mean, extend this talk further, but I was a little bit nervous, and that's why I
Yeah,
actually
right.
talked.
As I said, you are much young, very young.
Uh,
I was at your stage some maybe 45 years back, maybe more than that. So with experience, you will gain this understanding. But always remember that you have to keep attention of your audience in focus.
yes, sir.
So
Yes, sir.
so
Of
that
course.
if you put too much of information, people try to read one diagram by the time you go to the next, and then people may lose concentration. Secondly, this is on a lighter side, that this slide that you have right in front of me, somebody asked you a question that having 150 megapascal at a 5 kilometer depth or so seems to be a little unrealistic. In this case, I'll just on a lighter side, I will say when I was teaching thermodynamics here before I retired, then I gave an equation and asked them to plot a pressure temperature diagram with some data that I had already given. One of the students, IIT students are sometimes they really outsmart their teachers. So he produced a diagram with temperature range of minus 5000 K to plus 5000 K. So I struck it off but gave him full marks. So this fellow comes and says, Sir, my answer is correct. Why did you cut it? I said, this is your wrong answer, but I gave you the full marks. So why? Because I said, for your, the credit goes to you that you quickly realized that equation can be a straight line equation. And you took minus 5000 K, which does not exist in, in the, and also 5000 K, it doesn't happen in the metamorphic, in the geological context. But his answer was correct. So this diagram may be a theoretical diagram, but sometimes people can ask that why do you have 150 megapascal at 5 kilometer depth? Because you are essentially talking about stress at a very near surface phenomenon. And so take care of this situation in future. But your talk was very good, very nice, and at such a young age, you are giving such a beautiful talk. And it is obvious to me that you have done a lot of work, a lot of work.
Thank you, sir.
There is no doubt about that. And I must say thank you for such a wonderful presentation.
Thank you, sir. It really means a lot.
Okay. Any further questions? Okay. If not, then thank you very much, Deep. Um, I hope you have taken the comments down and written them properly, and then we will discuss later on, and we'll try to incorporate them before you submit your
Yes,
thesis and
yes,
work further. And thank you everyone for joining us today. I will send the notification for the next meeting pretty soon. Thank you very much.
Okay.
Bye. Bye.
They're very good.